I would like to thank the organizers for having invited me. And so okay, oh, there is a very small delay here. Okay, so the idea is the following. We were dealing with the Lorenz system. Actually, let's think to a problem in meteorology. We want, in general, to be able to have a simulation on our computer, no? And suppose that you have a good model of what is the atmosphere, no? The system that you are modeling. But clearly, you have the problem of finding the state of the system. Since in general, these are chaotic systems. So you have to perform some measurements on your system and synchronize your simulation with the data coming from experimental measurements. And the following problem is how to find the exact values of the parameters, because clearly you may have some vague idea of the real parameters, but you are not sure that your real system. Now, suppose, for instance, a very simple case. You have an electronic circuit simulating, I don't know, the Lorenz system or some equation like this. You put your components there, but you are not sure that the capacitor has exactly this capacitance, resistors has exactly that value, and so on. So you have these two problems. Okay, this is a more or less the idea, no? To have a simulation system synchronized with the real system. And clearly, you want to do this for two reasons. First of all, to perform measurements that you cannot perform on the reality. And second one, for meteorological system, especially we are concerned with nowcasting. So forecasting what is going on in the next few hours, because clearly you can make your computer go faster than reality and then use it for performing measurements. So you know the Lorenz system, so I skip this. And actually, this is essentially for a pedagogic reason that for this exposition, I would simply use the simple Euler scheme for integration, since essentially for chaotic system, unless you are performing very precise measurements, the effect of the algorithm is very little. And so we started from the idea of Pecora-Carroll. It was an old paper about 89, I think, in which they used to synchronize two electronic systems, two electronic circuits, by picking one signal from one circuit and injecting it into another one. And actually, there is a possibility, essentially, if you are working on, so I skip all this because you know a lot of this thing. And so the idea is that Lyapunov exponents and the synchronization system and the synchronization strength, in some sense, are related, in the sense that when you measure the Lyapunov exponent, you perform a small perturbation and you look how this perturbation expands. When you perform synchronization, you are pushing one system towards the other. Clearly, they are two related aspects. And in fact, for instance, if you push all dimensions, all the degrees of freedom in the same way, there is a very nice relationship between the synchronization threshold and the Lyapunov exponent. This is not true if you, so you can expand it, you can extend this to continuous time, but the problem is that when you are not pushing everything with the same rate, no, because you are, suppose you have a map which is simple to understand. You have a phase in the tangent space. You have a phase in which your map is expanding, and then the phase in which you are pushing. Clearly, if C, the pushing, commutes with the Jacobian, it is the same as performing before the product of all Jacobians and then the product of all pushing, and so you get the the relationship between synchronization and Lyapunov exponent. But if you are pushing, for instance, only one direction, say only in the X, like Pecora and Carroll did, they pick up the X value from one system and they inject all the signal in the other. They do not commute, and so you have different results depending on how you push. And actually, so you can define, I say, this is not mine, it is Pecora and Carroll, these conditional Lyapunov exponents. And so you see that in some directions, for instance, in X and Y, you can, these are X and Y, you may have a negative product at the end, so you can actually synchronize, while for instance in the Z direction you cannot. And this has also some nice consequence, but I will skip this. So now let's try to port this to a real system. So we have, first of all, the general problems are, I generally cannot really decide which degrees of freedom I can measure in the real system. In general, it is even more plausible that I measure a combination of different degrees of freedom. So for instance, let's suppose, let's talk about the Lorenz system. I have X, Y, and Z. Now, suppose that this is implemented in reality. It's a good model of reality. I cannot assume that I can measure X or Y or Z on a real system. Maybe I can measure X squared sinus of Y or something like this. Second, I cannot assume, unless I pick a wire from one circuit and put it into another, that I can measure things at any rate. Clearly, my measurement system has a certain bandwidth, and so I can perform a measurement every, I don't know, second, every hour, every day. No? And so we examined all these problems. And so, for instance, we see that, which is quite understandable, if you perform measurements out every delta t, it is like having a Lyapunov exponent multiplied by delta t, because clearly it expands for a certain amount of time. And so actually you can synchronize also using intermittent synchronization. So instead of pushing the system always together, you can push them only after a certain interval. This works clearly if you have enough. So if the time is small enough, the distance at a certain point drops to 0. Clearly, depending on the direction also. And we can scale and get some nice relationship, essentially replacing the Lyapunov exponent with the Lyapunov exponent multiplied by the interval. But now let's skip to the problem of finding the parameters. What happens if I try to synchronize two systems that do not have the same parameters? I do not get the full synchronization, I get phase synchronization. The systems stay close, but clearly they do not synchronize completely, because now as soon as I stop synchronizing, they diverge again, because only because of the difference of state, but because of the difference on parameters that will reflect on the difference in state. But then I can exploit this phase synchronization to find the good parameters. I mean, I measure the distance and then I optimize the system so that this measured distance above the synchronization threshold goes to 0. And if I'm able to do that, I'm pretty sure that I get the right parameters. So this is essentially what we did using, for instance, simulated annealing, since I can show you, this is for pedagogic, the actual shape of the difference is quite weird. So better to use some robust scheme, like, for instance, simulated annealing. And actually, we see that if everything goes well, this is essentially the temperature of the simulated annealing. When temperature goes to 0, the difference go to very small, very small difference from the real parameters. Okay, this is very nice, but this all again assumes that I'm able to measure the coordinates of the system, the real coordinates of the system, which is not really possible for every system. So now let's suppose that I can measure only a function of the parameters and not a single parameter. So as I said, x squared, sinus of y, or whatever. What is interesting is that I can take profit of the of the Takens theorem of the reconstruction of the attractor that says that a lot of quantities, like for instance the Lyapunov exponents, are quite robust with respect to the transformation of parameters and using a time series with delay as an embedding space. So the idea is to have a family or ensemble of replicas. Maybe this is the more visual way. Let's suppose I have an ensemble of replicas. Each replica has its own state variables and parameters. Then I let them evolve for a certain time, and then I perform a kind of genetic algorithm. I measure for this time here the distance between the state parameters of the system and those of the real system. Then I throw away the replicas that are too far, and I duplicate with some variation those that are near to the system. And indeed, after repeating this for a certain number of times, and I shall spend a minute after this discussing this point, if I have the good measurement system, I shall explain in a while, then I finally get an ensemble of systems that are quite close to the master one, and from which I can get the real value of the parameters and of the state system. What are the good systems? This is very related to the problems that we saw before, that, for instance, I cannot use every variable to synchronize the two systems. And I don't, okay, this is a, I have all the animation, but I'm going to skip it because this is not my computer. So essentially, this is the idea. This is the master one, which is going not to throw. These are the initial set of replicas. These are those that are thrown away, and these are those that are duplicated. After a while, you have a bunch of replicas that are following your real system. And the problem is, what is it? It depends, essentially, you can see it here. The fact that you cannot synchronize the Lorenz system using the Z variable is because these two lobes are essentially at the same level of Z. Oh, okay, so if this essentially the Z axis is in this direction, very perpendicular to the two leaves of the Lorenz system. So essentially, when you measure the Z, you cannot distinguish if you are in this lobe or in this other lobe. No? And so you can essentially you can synchronize a replica that is here to a replica that is going in this direction, and they remain at the same distance even though they are pushed together, because you are no, you don't have you cannot resolve this say this symmetry. And this happens, for instance, if you take two Bernoulli maps, it's the same. You cannot synchronize the two Bernoulli maps because for the same values of the y, you have two branches with exactly the same value. So it may happen that one replica is on one branch and the other is on the other one. And so this has the consequence that I cannot use any function of the three variables. There are some functions that are more symmetric and so cannot be used, and others that can be used, which is quite trivial, but you discover this after having performed a kind of simulation and say, why this is working and this is not working, and so on. Okay, so I try to be fast in order to recover some time. And so the conclusion is this one. Clearly, we can use this master-slave scheme for other systems. We are now trying to apply this both to electronic circuits and to real measurements. Clearly, for the moment, this has been done on a one dimension, so essentially on a local system described by only 3 degrees of freedom. We have still to start working on really extended systems like coupled systems, coupled maps, and so on. And then we actually can use this with a kind of genetic algorithm or pruning and enriching as you want in order to be able to extract variables and parameters from data coming from a real system. Clearly, all of this depends on how precise are your measurements, because if you add noise on this, everything goes down. And clearly, the other approach that can also be mixed with this is that based on artificial intelligence, as usual deep learning, so which is essentially using a black box in order to have your system. And so we clearly this is a competitor, and we are also trying to see if they can be combined together. I think that's all.
We recovered some minutes on the initial delay. So maybe if there is one very fast question, we can.
Question, Franco. As you know, when you apply the embedding theorem, you must, at 2-time series, you must choose the embedding dimension and the lag time. How this impact?
I know they impact a lot. Clearly, they have to be, as usual, spaced enough in order to be able to recover all the complexity of your tractor. Because clearly, if you are using too small delay, you are not. So you need a longer, say, time series. So there are a lot of technical questions that we have to study with with attention. But if you use long enough delay, depends on clearly on the complexity of your system. We observed that we were able to recover parameters. Then the limits of this technique has still to be determined.